In this lesson, we're going to study a different type of discontinuity, an infinite discontinuity, and you'll see in a moment why it's called that. We're going to consider a new parent function, y equals 1 divided by x. If x is 3, y is equal to 1 divided by 3, or 1/3. And if x is 2, y is equal to 1 divided by 2, or 1/2. What you'll notice is the output values, or the y values, are just the reciprocals of each of the x values. Now when we get to 0, 1 divided by 0 is undefined, so that's not going to produce a y value because x equals 0 is outside the domain of this function. And then we have our negative values. The reciprocal of negative 1/3 is negative 3, of negative 1/2 is negative 2, negative 1, negative 1/2, and negative 1/3. We can plot all these points. When x is 3, y is 1/3. When x is 2, y is 1/2. When x is 1, y is 1. When x is 1/2, y is 2. And when x is 1/3, y is 3. And what you'll notice about this graph is that it behaves asymptotically. That is, that the graph approaches both the x and the y axes. And the same is going to be true when x is negative. When x is negative 3, y is negative 1/3. When x is negative 2, y is negative 1/2. Negative 1, comma negative 1, negative 1/2, comma negative 2, and negative 1/3, comma negative 3. And that's going to produce a very similar looking graph, but in the fourth quadrant. So this graph, which is called the reciprocal function because the outputs are the reciprocals of the inputs, has what we call an infinite discontinuity. And it is called an infinite discontinuity because of this asymptotic behavior. Now, the y-axis is what we call a vertical asymptote to the graph, and the equation of that y-axis is the equation of a vertical line, x equals a number, and x equals 0. So the vertical line with equation x equals 0 is a vertical asymptote because as x approaches 0, y approaches either infinity or negative infinity. There is also a horizontal asymptote to this graph. That's the x-axis, which is a horizontal line, so its equation will be y equals 0. And y equals 0 is an asymptote to the graph because as x approaches either positive infinity or negative infinity, the y value approaches 0. And that is talking about the ends of the graph. So the right end of the graph, our x values are getting larger and larger or approaching infinity, and the left end of the graph, the x values are getting more negative, which means they're approaching negative infinity. The graph of this reciprocal function is called a hyperbola, which is one of several quadratic relations. A parabola is one of those types, and that's like y equals x squared. This is a very special type of hyperbola, though, and you won't see that quadratic relation in this particular one. All right. That being said, we can graph a transformation of this parent function. When we take the parent function and we replace x with x minus 3, that moves our graph right 3. And when we add 2 to the output of the parent function, that moves the graph up 2. So the vertical and horizontal asymptotes, which were at the x and the y axes, are going to move right 3 and up 2. So the new intersection of those axes will be at the point 3, 2. So I'm actually just going to sketch in our vertical and horizontal asymptotes. The vertical asymptote will be x equals 3, and I usually graph that with a dashed line to indicate that it is not actually part of the graph of this function. It's just a guide to the graph. And then we have a horizontal line here. That horizontal line has an equation y equals 2. So again, we'll graph that with a dashed line. And now, in addition to the asymptotes, we want to graph one anchor point per branch. That'll be sufficient to show the shape. So in order to find out what the values for those anchor points are, I'm just going to make a table of values for x and the y value, which is 1 over x minus 3 plus 2. And I'm going to pick an x value that's to the left of that vertical asymptote. So if the vertical asymptote is at x equals 3, a point to the left would be x equals 2, and a point to the right would be x equals 4. When x is equal to 2, the y value is 1 over 2 minus 3 plus 2, which is negative 1 plus 2, or 1. And when x is equal to 4, the y value is 1 over 4 minus 3 plus 2, which is 1 plus 2, or 3. So when x is 2, y is 1. And when x is 4, y is 3. And now, since we have the asymptotes, we can fit the graph to those guides fairly easily with that one anchor point in mind. Make sure that when you graph these, that your graph is moving toward the asymptotes as the graph continues. It should not be sweeping away like this, for instance. So I'm going to get rid of that because that's incorrect. All right, let's check out the example for b here. G of x is equal to negative 1 over x minus 1. So since we've replaced x with x minus 1, the graph will move 1 to the right. Since we don't have anything added to the outside of this function, we're going to move up 0. So just a translation to the right. So that means that our vertical asymptote will be at x equals 1 and horizontal asymptote at y equals 0. I'm going to go ahead and sketch those two asymptotes in. X equals 1 with a dashed line and y equals 0 with a dashed line. In order to figure out what points go on the graph, I'm going to pick points that are to the left and to the right of x equals 1. To the left would be x equals 0, and to the right would be x equals 2. And our y value will be negative 1 over 0 minus 1, which is positive 1. And for x equals 2, the y value is negative 1 over 2 minus 1, which is negative 1. Graphing those 2 points, 0, 1, and 2, negative 1, that's enough to give us a good idea about what the rest of this graph looks like approaching the asymptotes as we move from that anchor point. For the next example, h of x is equal to 3 over x plus 2. So replacing x with x plus 2 is going to move this graph left 2, which means our vertical asymptote will be at x equals negative 2. And the minus 1 on the outside is going to move us down 1. So our horizontal asymptote will be at y equals negative 1. I'm going to go ahead and sketch those two in. So we have x equals 2 and y is equal to negative 1. Once we've sketched those in, I'll use a table of values to locate one anchor point per branch. So for our first branch of this hyperbola, we need to pick a point that's on the left side of x equals negative 2, which would be x equals negative 3, and one on the right side, which would be x equals negative 1. So when x is negative 3, 3 over negative 3 plus 2 minus 1 is negative 1 minus 1, which is negative 2. And then for x equals negative 1, 3 over negative 1 plus 2 is minus 1, which is 3 over 1. 3 minus 1 is 2. And I just realized I made an arithmetic mistake up here. 3 over negative 3 plus 2 is negative 1. Is not negative 1. 3 over negative 1 is negative 3. Negative 3 minus 1 is negative 4. Sorry, long day. All right, so negative 3 -3 comma -4 is down here, and -1 comma +2 is down here. I realized I made another mistake. Yay! My other mistake was the vertical asymptote was at x equals -2, not at x equals +2. That's better. Now we can graph in the remaining portion, which is going to look like that. That times 3 up in the top gave us a vertical stretch on this graph. Okay, it's your turn to try. Try D on your own and pause the video while you do this. All right, here's what you should have gotten. Now let's move on to combining infinite discontinuities with removable discontinuities. So in example 2, we have a function that can be written in simplified form. So g of x is equal to x minus 2 divided by x squared minus 3x plus 2. This can be simplified by factoring the denominator, x minus 2 times x minus 1, and when we simplify, we can remove that factor of x minus 2. That's going to produce a removable discontinuity. When we factor and cancel, that will leave us with a simplified form of 1 over x minus 1. But now we have to state explicitly that x cannot be 2 because it's not obvious by looking at the function at this point. But in the original function, x was not allowed to be 2, x was not allowed to be 1. So there's our simplified form. And then we are going to have a removable discontinuity at x equals 2. We'll figure out what the y value is for that removable discontinuity in just a moment. And if we look at g of x equals 1 over x minus 1, that's a translation right 1, so there will be a vertical asymptote x equals 1. There is no translation up, so the horizontal asymptote will be y equals 0. All right, let's create a table to find points on this graph, just like we did with the other transformations of the reciprocal function. Our y values are 1 over x minus 1. And so we're going to pick a value on the left side of the vertical asymptote, on the left side of x equals 1, that would be 0, and 1 on the right side, that would be 2. When we pick x equals 0, that's 1 over 0 minus 1, which is -1. When we pick x equals 2, that's 1 over 2 minus 1, which is equal to 1. However, you might have noticed that x equals 2 is the location of our removable discontinuity, or the hole in the graph. So the hole in the graph has a y value of 1. We need to make sure to indicate that with an open circle when we graph. All right, let's plot the asymptotes to the graph. The asymptotes to the graph are x equals 1 and y equals 0. And we have 2 points to graph. We have a 0, -1 on one branch of the hyperbola, and a 2, 1 that is a hole in the graph. But that's enough to give us an idea of basically what this function looks like with the removable discontinuity, or the hole in the graph, noted. In B, we can simplify this function by factoring the denominator, x times x plus 3. And when we write this in simplified form, h of x is equal to, canceling the factors of x, will be 1 over x plus 3. But we need to acknowledge that we removed a discontinuity when we did that, so we need to state that discontinuity explicitly for x not equal to 0. So that means we'll have a removable discontinuity when x is equal to 0, and since our denominator of x plus 3 is intact, we'll have a horizontal asymptote of x equals -3. Since there's no translation upward, y equals 0 is the horizontal asymptote. So now I'm going to pick an x value that's on the left side of -3, that would be -4, and one on the right side, -2. And then we've also got to find out what the y value for the hole is. So when x is negative 4, 1 over negative 4 plus 3 is negative 1. When x is negative 2, 1 over negative 2 plus 3 is positive 1. And when x is 0, 1 over 0 plus 3 is the y value, and that's 1/3. So let's graph the horizontal y equals 0 and vertical x equals negative 3. Those are our asymptotes, and we have one point on the graph at negative 4 comma negative 1 and another at 2 comma positive 1, and we also have that removable discontinuity at 0 comma 1/3. And now we can just sketch in the rest of this reciprocal function. All right, the next one is for you to try on your own. Please pause the video while you do this. All right, here's what this graph should look like. You notice this one worked out differently because when we removed the discontinuity at x equals 1, we were left not with a reciprocal function, but with a linear function instead. So the graph is of a line, but when you create your table of values, when we replace x with 1, that's the point where we have a removable discontinuity or a hole in the graph because x is not allowed to be equal to 1. Let's take a look at our last example. G of x is equal to x cubed minus 9x divided by x squared minus 9. Now I can factor an x from the numerator and we get x times x squared minus 9 over x squared minus 9. Before we get tempted to just cancel, I'm going to factor a little bit further. X squared minus 9 factors to x plus 3 times x minus 3, and the 1 on the bottom does as well. But I think when we factor it, it becomes obvious that there are actually two values that x is not allowed to be for this particular function. So when we rewrite, g of x is equal to x once we've canceled common factors, but for x not equal to either positive or negative 3, so there will be two removable discontinuities, one at negative 3 and one at x equals positive 3. And this turns out to be a linear function, so no vertical asymptote, no horizontal asymptote. And if g of x is equal to x, that's basically y equals x. So when x is negative 1, y is negative 1. When x is 0, y is 0. When x is 1, y is 1. So our removable discontinuities are negative 3 comma negative 3 and 3 comma 3. So we've got a straight line. Let's graph some points. So we definitely know that we have points negative 1, 0, 0, 1, 1. We have removable discontinuities at negative 3 comma negative 3 and positive 3 comma positive 3. And so this is just going to be a line at 45 degrees through the first and third quadrants with two holes or removable discontinuities.